Good afternoon. So this is Transport 2, exam number 2. The problem that we have today, we have a nice little evaporative mass transfer action going on here today. So we have as a tube, we have the gas evaporating upward, and then the liquid falling down, cooling, or heating up as it flows down. So what we want to find today is a couple different things. First thing we're going to do is do the dimensional analysis. That's going to be this very first part here on the whiteboard, because we want these three dimensionless groups. While I'm trying to deal with a big problem like this, there's a lot of variables. We have Kc, we have the viscosity, we have the density, the diffusive coefficient, even the diameter of the tubes. And with all those variables, there's a lot of different dimensions that you're going to get into. I mean, there's up to 6 dimensions, and you can't really visualize that graphically. So what we're going to do is do some dimensional analysis in order to define these three-dimensional groups. And then these three-dimensional groups will later be used to fit data in the form of this equation here. And what we're going to do is plot that on Python, and after we plot that on Python, we'll have a nice little interactive graph that we'll be able to mess with, and will be a lot easier to visualize than like 6 dimensions and some crazy stuff. So what I'm first going to do is define what all these variables actually are in their units. So Kc is just meters per second, and I put that and velocity next to each other because velocity is also meters per second. Density is kilograms per meters cubed. Viscosity is kilograms per meters per second. The diffusion of A and B is meters squared per second. And then the diameter is obviously just meters. So what we're going to do with all these here is do a little table, and then we're going to get a matrix, and then we're going to use this matrix to find out how many dimensionless groups we need. We already know it's 3, but I want to prove it. We're going to need 3 dimensionless groups, and then we're going to use these units here to come up with our dimensionless groups. So what we're going to do first is we have meters, we have seconds, and we have kilograms. These are our three kind of SI units that we're using. And we have Kc, velocity. I'm going to rewrite these over here. And then we're going to kind of see how many of these units are in these units. So in Kc we have 1 meter, minus 1 second, and then 0 for kilogram. Same thing with velocity. Density, we have 1, minus 3, 0. Viscosity, we have 1, minus 1, minus 1. We have 2, minus 1, 0, and then with the diameter, we just have this. So this gives us a nice little matrix right here, and what we're going to do with this matrix is that we're going to put this matrix in the form of this equation I, which is the number of dimensional groups that we need, is the number of variables we have right here, minus r, and r is a constant I'm going to find in a Python real quick just to kind of show you guys how I get that. So what we're trying to do here is find the rank of our nice little array that we had. If you remember on the whiteboard like 30 seconds ago, there was an array with a bunch of 1s and 0s, a bunch of negative 1s and 0s, blah, 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 correlating to each of our various dimensions, each of our variables, and then with the meters, kilograms, and seconds. So what to do, we had that equation I is equal to n plus r, and or n minus r, and we remember that I is the amount of dimensional groups that we want to find. N is the amount of variables that we have. We already know we have 6, but we need to find R, which is the rank of this array. So in order to do that, we're going to code something out because it's pretty hard to do with pen and paper. So we're going to import a little bit of numpy, np, load that up real quick. I'm going to make my array just called AR, and that's going to be equal to np array. And then for my array, I typed it out in notes right here, so I didn't have to do that and take up more time right here, or keep looking at the whiteboard back and forth. So that is the array that we're going to have. And then after that, we're going to numpy, then elge, and then what is it? Rank, matrix rank of AR. So what is our matrix rank? 3. So R is equal to 3. Just this little simple code right here. We took our array and then put it into a little linear algebraic matrix rank thing, and output is 3. So R is equal to 3, and we will solve the rest of this on the whiteboard. Perfect. So I just showed you guys how to find R, the rank of the matrix that I erased because it's going to take up too much room. But I'll just show you how to find the rank of that, and the rank is 3. So that means that I is going to be equal to 3 because we know that n, the number of variables, is 6. There are 6 variables here. 6 minus 3 is I equals 3. So we know that there are 3 dimensionless groups that we kind of have to find to kind of characterize this problem properly. And to define these 3 dimensionless groups, what we're going to do is indicate them by pi. So we have pi 1 that we're going to try to find, pi 2, and pi 3. And in order to find these 3, we kind of have to cancel out units to find groups that are dimensionless. So we need 3 core groups here. And the 3 core groups that we're going to use are Kc, the velocity, and the viscosity right here. So we're going to have Kc, and these are going to not be repeated throughout when we do this analysis. So now that we have these 3 core groups here, we have to fill them in with the rest of the respective variables. So we have the density, diffusion, DAB, DAB, and then we have the diameter, and then we're going to also have exponents in all these, A, B, and C, and D, and E, and F, G, H, and I. And these exponent variables, we're going to try to find systems of equations, and we're going to solve the system of equations of each unit to cancel them out and make sure that we have our dimensionless groups, pi's 1, 2, and 3, to be truly dimensionless. So I'll kind of show you what I'm talking about in a second. So for example, we're going to do pi number 1, dimensionless group number 1, and the Kc units are meters per second. That's going to be multiplied times the density right there, kilograms per meters cubed. The fusion constant is, diffusion is meters cubed over seconds. I was looking at viscosity there, and then the diameter is just meters. So we have here, we're going to try to find a system of equations, and we want the system of equations for each meters, kilograms, and second for each unit to be equal to 0, because we want a dimensionless group to properly characterize this problem. So for example, for meters, we're going to have this set equal to 0, and we're going to have 1. This is in the numerator. 1 plus 2, what is that, B? I should have started with A, oh well, but minus 3A plus C. And we can't solve this yet, we got 3 variables, we can't solve that equation yet. This is the first system of equations we have here, and that's for meters. For seconds, we have 0 is equal to negative 1 minus, what do we have here? We have B, minus B. And then for kilograms, we only have 1 kilogram unit here, and that's in A, so 0 is equal to A. So we know that A, this exponent here, is equal to 0 because there's no kilograms to cancel it out with to make a dimensionless group. So A is going to be equal to 0, so I'm going to swap this out for 0, and then B minus 1, we're just going to put that B on the other side. B is equal to negative 1, so I'm going to make this negative 2 so we can solve it. Negative 2 minus 0 plus C, we're going to put that's going to be negative 1 over here. C is equal to negative 1. So we have B to be equal to negative 1, C to be equal to negative 1, and A to be equal to 0 to kind of have this, this dimensionless group here. So that means that pi 1 is going to be equal to Kc, and then on the bottom, B is negative 1, so the diffusion of A and B, and then C, the diameter. So this is the dimensionless group number 1, and this is actually C equal to the Schmidt number. I don't know how to spell Schmidt, but that's the Schmidt number. So what we can do all that entire thing for pi, for the second dimensionless group as well, but we know that the velocity is equal to the same exact units as Kc, so what we're just going to do is pi 2, the second dimensionless group, is the same exact thing except velocities on the top instead of Kc. So velocity over the fusion constant times the diameter, and that is our second dimensionless group, and this is PR. Perfect. That's the second number that we wanted to find. We're getting to that. But the third dimensionless group that we have down here, we have viscosity, so we're going to have to do the same exact thing again because the units are a little bit different. So we have kilograms on top, meters times seconds on the bottom. And then we're going to do the same exact thing that we did for dimensionless group number 1. the Schmidt number for number 3 as well. So for the density, we have kilograms per meters cubed. The fusion of A and B, meters squared over seconds. And then, can you guys still see me? Perfect. And then we have the diameter again, which is just meters. So we have, for meters, we just have 0 is equal to -1. We have minus 3a plus 2b plus c. And again, we can't solve that yet because there are 3 unknowns. But for seconds, we're going to have 0 is equal to, we have -1, sorry, minus b. So we know what b is. B is going to be equal to, same exact thing as before. B is going to be equal to -1, sorry. Because if you have b over there, b is equal to -1. Yeah, kilograms, 0 is equal to 1 in the numerator right here, plus a. So a is also going to be equal to -1. So I'm going to just put these out here. So we're going to have plus 3 on the top, minus 2. So 3 minus 2 minus 1 is 3. We put 3 on, or sorry, 3 minus 1 minus 2 is 0. So we're going to have 0 is equal to 0 plus c. So that means that c is equal to 0. So that means for our very last, can you still see this? Perfect. For our very last dimensionless group here, pi 3 is going to be equal to viscosity over b, which is the diffusion constant, dA and b, and then over a, which is g, which is the the density right there. So perfect. This is our third dimensionless group, and this is the Sherwood number right here. So we've characterized these 3 dimensionless groups. I'm going to erase a little bit of work and clean this up a little bit. We still have to find the Reynolds number, which is going to be the pi 2 over pi 3, but I want to clean this up, so give me a second. I just want to note, before I erased everything, I realized that this is -1, -1, 0 equals -1 plus c. That is not -1, that is 1. So c in this instance would be 1. That would put the diameter in the numerator, and then the Prandtl number would also have the same exact thing, the diameter in the numerator. My mistake. I just wanted to clarify that before I erased everything. Yeah, so dimensional analysis is pretty easy, just a kind of a time-consuming busy work process. So I wanted to erase a lot of that busy work and focus on kind of the big concepts. So what we just did, we did all that work, and we found that dimensionless group 1 is equal to Kc over the diffusion, or Kc times the diameter is equal to the diffusion constant, or over the diffusion constant. That's dimensionless group number 1, and this is the Schmidt number. And then the second one here, we had velocity times the diameter over the diffusion constant. That's PR, Prandtl number. And then number 3 that we found, that was just viscosity over d A and b times the density, which is equal to the Sherwood number. Or, sorry, that's SH. However, we don't have a Prandtl number up here, and we do have a Reynolds number up here. So what the Reynolds number actually is the second one here over the third one, the Prandtl number over the Sherwood number. So what we're going to do, we're going to have over here pi over 2 over pi, or pi 2 over pi 3 is equal to PR over SH. That's going to be equal to velocity times the diameter times dA and b, and that's going to be multiplied times the reciprocal of number 3 right here, which is going to be dA and b, for the density divided by a little viscosity right there. And what we're going to find is that these two cancel out, and then we have a number that we all know and love, the velocity times the diameter times the density over the viscosity. And what that bad boy is the Reynolds number. And we know that from a lot of lectures in the past. That's what we use to find laminar and turbulent flow. And this is our final dimensional analysis, our final dimensionless group found through dimensional analysis that we're going to use in the second part of this exam to kind of find we're going to plot the Reynolds number, the Sherwood number, and the Schmidt number over 100 hypothetical data points. So that's coming up in a second, and that will be in Python. So just as a review, we did dimensional analysis to define these three groups, and now we're going to move on to part two, fitting the data in the form of this little equation right here in order to characterize this picture right here. So that is part two coming up now. What's up, guys? So this is the coding section of this problem. If you recall, in the very first problem, we just looking at the whiteboard, did the dimensional analysis and determined our three dimensionless groups, the Schmidt number, the Sherwood number, and the Reynolds number. And now we're going to use those three dimensionless groups to kind of create a 3D visual representation of this problem, so that if you change any of the parameters like the diameter or the viscosity of the fluid, then it would accurately reflect those three dimensionless groups. And in order to do that, we're going to create 100 pseudo experimental points and then just kind of do a bunch of Python stuff and that I will explain and get our 3D model representation. So to start, I imported these functions. I didn't want to type them out because it's kind of counterintuitive. Of course, we always have numpy, our three plotly subplots that we used in the last video as well to make our subplots and then be able to add objects to them and then be able to edit them. And I already started off with the pi-o just to make the plotly dark because I think the dark will look a lot better contrasted on the white Google Colaboratory background. And we also want to do, we're going to have a little bit of error in this problem with our experimental data. And as we do a sum squared minimization to kind of reduce this error, that's the function that I imported right here. So we have skippy, optimize, import, minimize. So the very first thing we want to do is create our experimental data. And the Reynolds number, if you recall, I'm going to just import numpy, numpy random, and then it's going to be, what is this? Not general, but uniform stacked data. And if you recall, the Reynolds number that we have right here is 2000, so 2e to the third, as well as, what was it, 35,000. So for 35e to the third, and so those are going to be our two parameters within the Reynolds numbers, and then we want 100 of these different data points. So the same thing for the Schmidt number, copy and pasting because I'm lazy. The Schmidt number is between 0.6 and 2.5 inside the problem parameters, and we're also going to have 100 of those data points as well, and that is the Schmidt number SC. And for the Sherwood number, I just want to make sure this is working so far. No problems, but you never know. The Sherwood number is going to be this equation. If you recall this very equation that we have right here. So the Sherwood number is going to be 0.023 multiplied by the Reynolds number to the power of, what was it, 0.83. 0.83, and that's going to be multiplied times the Schmidt number of, I believe it was 0.44, but just let me double check. Yes, 0.44. So that's going to be the Schmidt number. So for each value of the Reynolds number and the Schmidt number, we have a value of the Sherwood number, and that's going to be given in an array. So if I typed out the Schmidt number right here, it's going to be a big array of all that stuff plugged into the problem. So we also have a little bit of error. We have the correlation of a 10% normally distributed experimental error that is in this problem. So in order to add a little bit of error to this problem, we're going to redo the Sherwood number, and that's going to be as numpy random normal. So we have a normal distributed error that we're about to have right here. So this function right here is given by the LOC. That's just going to be the function that we have. It's going to be the Sherwood number, and then the scale of the function is going to be 0.1 because we have a 10% error, and that's going to be multiplied times the Sherwood number. So we don't just have 10% error of nothing, you know? So it's the very first part. If we redo that there are no problems. Perfect. All right, guys, so quick side piece. I just wanted to go through the linear algebra matrix math to show you guys how we're going to actually determine what A, B, and C are. Remember, this is our model that we're going to have with the Sherwood number times A, times the Reynolds number to the B power, times the Schmidt number to the C power. And what we want to do, we want to find out what A, B, and C actually are for our data set. So I'm going to show you guys how to actually go through and actually find this. So the first thing we're going to do, we're going to take the natural log of everything. So we have the natural log of the Sherwood number is equal to the natural log of A. And we got natural log properties here, so that's going to be added to B, natural log of the Reynolds number, plus C, the natural log of the Schmidt number. And remember, what we want to find is A, B, and C. And what we have here, this transposes, this is going to exactly correlate to a matrix that we have over here. So we're going to have a matrix with ones all the way down. There's going to be 100 values because we have 100 pseudo experimental data points. So we're going to have ones all the way down here corresponding to that. And then we're going to have the natural log of the Reynolds number all the way down, all of the values for that. And the natural log of the Schmidt number, values all the way down for that. And this is actually going to get multiplied by something that we're going to call U. And what U is A, B, and C. So it's going to be the natural log of A, the natural log of B, and the natural log of C. You guys see that? You guys can. Hang on. There, so the glare is not as bad. Perfect. So we're going to have this stuff here multiplied by that. And what that is going to give us, when you multiply that times that together, that's going to give you the natural log of the Sherwood number, because we're going to follow this. It's going to spit out what this model wants us to have. So this is going to be the natural log of the Sherwood number all the way down for all 100 values when you multiply U by our matrix right here. So what this basically follows kind of is that X, we're going to call this entire, I'm out of space. We're going to make this X. So we have X right here, and X is multiplied times U, and that is going to equal the natural log of the Sherwood number. So that's what we have right here. So we're going to have the natural log of the Sherwood number for this matrix area right there. So what we want to do is get U by itself, because U represents A, B, and C, and those are the guys that we actually would like to find. So, and this lighting is awful. There we go. U is what we want to find. So with matrix rules, we're going to multiply first by the transpose. So we're going to put the transpose of X on both sides. And that's going to give us X times X of the transpose times U. That's going to equal transpose of X times the natural log of the Sherwood number. And now to get this along, we're just going to multiply this times the -1. So we're going to have U by itself is equal to xt, natural log of the Sherwood number, multiplied by xt x to the -1. So I just wanted to show this math out. This is how we're going to get U, and this is what we're going to be using linear algebraically. I'm going to reference this in the code in a couple of minutes. So when you see me look at the whiteboard, this is the equation that I'm looking at right here. But I just wanted to do the math out here because it's a lot easier than explaining it on Python. So we just on the whiteboard, we're going to have to do some linear algebra here in a second. But currently, I just want to point out that we have everything kind of in like their own different matrices. So if we had the Sherwood right here, we have a ton of numbers, which is all fine and dandy. We can play with those and do error on this stuff, but they're not juxtaposed with the Reynolds number and the Schmidt number, and that's what we want. So what we're going to do is we're going to create a new variable X, and that's just going to be the numpy column stack of all of these different variables. And what we're going to do, we want a column stack. The very first thing we want to column stack is numpy ones like, because as you saw on the whiteboard, all of the very first column in the matrix is just a bunch of ones. So it's going to be ones like, and the ones like function just creates a row of, or a column of ones with how long you want it to be. So we want it to be as long as the Reynolds number. So column stack, this should be a bracket, and then this should be a comma, because the next thing that we're going to do is, yes, the log of, so np log of the Reynolds number. So we have the log of the Reynolds number in the next column, and then we have the log of the Schmidt number in the next column. So what this is going to do is brackets, parentheses. That's the hardest thing about coding, is seriously just getting the parentheses and everything together. So you have no errors there. So now we have a stack of columns like we did on the whiteboard, and that's just going to have the ones, the log of the Reynolds number, and the log of the Schmidt number all the way down to 100, because that's how many data points we have. So the next thing we're going to do is we're going to make another variable B, and this is just going to be, eventually this is going to spit us out A, B, and C, because that's what we really want. We really want A, B, and C of A, B, and C right there. So we want to find those values for this specific set of experimental data. And we're going to do this by a little bit of linear algebra. And then we're going to, we have the very first thing is the inverted of X, transpose of X, times you do the transpose in Python by just point T, and then you multiply matrices in Python with the at symbols. That's pretty sick. So add those two, and that's going to be another at. And then we have another transpose of x, and then we have the log, log of the Sherwood number. Because that is what we are trying to find. So perfect, after we do this, there should be no errors. Perfect, there are no errors. And now if we print B, we have the sick little array. So this sick little array, this is the this is the natural log of A. So what we're going to do in a second is do this to the E power to get our actual A. This is our B, and this is our C. So if you notice, this is strict. These values are pretty close. They're not exactly spot on to the established values for this equation, but they're pretty close. And the reason they're pretty close but not exact is because they're tailored to this specific set of data. So if we refreshed all these again, you get a little different numbers because the data is going to be a little bit different because it's random, but at the same time, it's still close enough to have in respect to those values. So the next thing we want to do is we're going to set B 0, which is the very first value of this array right here. B0 is going to be equal to the, like I said, the exponent, so e to that power of B0. Perfect. So now if we reprint B, then B is this value. This is our A value. This is our B value. And this is our C value. Again, they're very close to these values that we have here. So this is going to be our experimental data. Sweet. So now that we have our array with our A, B, and C values, we want to cut down on the amount of error that our experimental data has given us. And we're going to do that with a sum squared error with also using the minimums function that we imported earlier. So the first thing we're going to do is define our function. We're going to do sum. We'll just do a sum sq error. And then we're going to use p as our variable. Don't forget the semicolon. And then this is going to give us a function called sum sq error. And what this is going to do, we're going to use this to future minimize it and try to cut out all of our most of our errors. So we're going to return. What we're going to return is, if you recall, the sum squared error is our current model, and it's going to be minus what the ideal model is. And the ideal model is just the natural log of it's going to be the P0, the very first value of P in the array that we have, plus P1 times the Reynolds number, plus P2 times the Schmidt number. So we're going to have our initial, model right here, which is just going to be numpy times, it's going to be the natural log of the Sherwood number, and that's going to be minus, don't forget these parentheses, it's the hardest part of the code, minus P0, and that's going to be multiplied times nothing, actually, that's just the thing by itself, and then P1 is going to be multiplied times numpy, the natural log of the Reynolds number, RE, and that's going to be added to P2, the third value in the function, times numpy log the Schmidt number. And I'm checking these parentheses to make sure it's fine. And then we end up right there. This is all going to be squared. So that should give us no errors. Love to see it. And what we're going to do with this function, sum sq error, we're going to minimize it with the function that I imported earlier. So we're going to bring in minimize, and then we're going to have sum sq error. And then we're going to have the second parameter in this function is the initial values. And what better initial values to use than the actual established values for this equation. So we're going to use 0.023, and then what were the other two? 0.83, and then they're up here as well. Whoops, 0.44. That's going to minimize our error, hopefully, and I'm going to put brackets around these. Whoops, just to be safe. Parentheses and brackets are hard, and that is going to give us perfect. This is going to give us the exact values that we had above here. However, our data set is now minimized. So this is all actually really cool, because what we have here is our A with the natural log of our A, which is negative 3.6. Remember, that was how it was up here before we took that to the E power, and then we have our B here and we have our C here. So this is really cool because we did a sum square roots and then used a minimization to kind of find the line of best fit. That's what we wanted here. We wanted a line of linear regression with the Penrose pseudo inverse, and we minimized the sum square deviation between the model and the data. This is how Excel does their best fit lines, and that's what we pretty much just did here. So perfect. All right, so at this point we have our second set of data right here, and I just wanted to make a point that we have our second model here, but I also wanted to make a point that if we go through and refresh like I have been, just to double check that even though the numbers change right there because we have a new set of experimental data, they are still very close to the established values up here. We have 0.83 compared to 0.83 and 0.85 compared to 0.84. They're very close to the established values, but also the same between the two models. So in using our sum squared minimized model right here, we still want to be able to graph these things. So we're going to have a figure, and then what we're going to have in this figure, we're going to make our subplots. That's what I imported at the very beginning up here. And then our figure, we want to add stuff. So we're going to add, trace, add trace, and PGO. We're going to add scatter. 3D plots. And in this, there we go. We have all of these different parameters that we want to have here. So we want our X values to be set to the Reynolds numbers. It's going to be RE. The Y values are going to be set to the Schmidt numbers, SC. And the Z values are going to be set to the important one, the RH number. Or SH number, sorry, Sherwood number. And perfect. After that, we also want to define what we're making. So our mode is going to be, we're going to have markers. Later on, we're going to have mode, but it's going to be in lines because we want to have that mesh throughout our model. So we're going to have markers. We can also make the marker size. Is it marker size? Yes, marker size is going to be, we're going to make it 4 because we want to emphasize the experimental data that we have. If you're in the real world, that's what you really care about anyways. And then we're also going to have the marker color be equal to our values for the Sherwood number. And what that's going to do is hopefully make a graph, or don't. That's fine. What do I have around here? Mode markers. There's an S in markers. Perfect. So now what we have in our data here, by setting that color equal to the Sherwood number, you kind of get this nice little gradient according to our Z, which is what we want because that's the Sherwood number. But here's our experimental data set in this graph right here, which is what we were looking for. Perfect. So now that we have our plots all on here, this is all of our experimental data and everything like that. But this isn't just what we want. We want to plot your data as 3D points, but also wireframe plots. We're going to have wireframe plots kind of indicating for any values of X, Y, and Z where the last one would correspond to. So if we had any values of the Reynolds number and the Schmidt number, where the corresponding Sherwood number would kind of go to. And in order to do that, we have to kind of just create this wireframe mesh around the entire data set. So we're going to use NumPy mesh grid, I believe. Yep. So NumPy mesh grid, and then we're going to use keep spelling this wrong. Line space to kind of determine our starting points and like where the lines are going. So this is going to create the lines, and then mesh grid is going to put them on corresponding to where they're going to be at on the grid. So I'm also going to define SC mesh and RE mesh to kind of put these values to. Perfect. So what we have here, we have our initial parameters of the Schmidt number, which is going to be 0.6 and 2.5 if you recall from earlier. So 0.6, 2.5, and the number of lines that we want, we're going to do 25 lines so that we have a nice thick layer of mesh that we can use. So that's for the Schmidt number. Now we're going to have for the Sherwood number, or the Reynolds number. The Reynolds number is, remember, 2,000, so 2e to the third, and 35e to the third as well. And we're also going to do 25 lines for the Reynolds number. So that should create that'll store mesh in the form of the Schmidt number and the Reynolds number. And what we want to do is we want to have one for the Sherwood number as well. So Sherwood mesh is going to be equal to our equation that we have right here. So we're going to use A, B, and C from our data set to create the mesh from the Sherwood data set. So if you recall from earlier, we defined A as this number right here. So we have our B array. So it's going to be the first item in that array, B0, and then that's going to be multiplied times it's going to be multiplied times the Reynolds number to the B1 power, and then that's going to be multiplied times the Schmidt number to the B2, which corresponds to, that's B, this corresponds to, forgot a B right there. This corresponds to A, B, and C, which corresponds to that equation right there. So that creates our mesh for the Sherwood number, which is what we're looking for to tie all of these together. And in order to actually properly tie all these together, this should be the mesh for actually all of these, because we want to tie them to the mesh. So the Reynolds number for the mesh and the Sherwood number, the Schmidt number for the mesh. Perfect. So what we actually want to do is we want to tie these all together, and Python has this thing called zip. So what we're going to do is kind of zip all these values together, and then eventually we're going to use add trace to kind of put them all together. So for each iteration of the giant arrays that contain all of the values for the Reynolds number, the Schmidt number, and the Sherwood number, we want to zip all these together so they can all get compared with each other, and we can have a comprehensive list of all of the mesh that's going to come onto our graph right here. So for I of the Schmidt number, for I of the Reynolds number, and for I of the Sherwood number, what we're going to have we're going to zip them together, and we're going to zip them together with their corresponding meshes. So the Schmidt mesh, the Reynolds mesh, and the Sherwood mesh. So for each of these, does 4 have a comma after or a semicolon? I'm pretty sure it does. So for each of these, for each iteration right here, we're going to figure and we're going to add trace. First one, let's go. We're going to add trace of each of these. It's the same exact thing that we had up here. So we're going to have PGO, scatter plot in the 3D. And for each of these, we're going to add, so for the X values, we're going to have the I with the Reynolds number, because the Reynolds number is the X value up here, remember. The Y value, we're going to have the iterations for the Schmidt number. And for the Z, we're going to have the iterations of the Sherwood number, which actually makes all sense, because what this for loop is doing is basically going through for each iteration in the giant array. It's going to plot a little line and just kind of like keep those lines going. It's going to make a mesh, and that's what we wanted. So our mode that we want to have, we want lines. And our line, we'll do line color is, we'll make it white so it juxtaposes on the nice black, oh my god, where's the apostrophe? On the nice black background. So what this code should do, looking over it real quick before I get mad when it doesn't work, it should create, perfect, no errors, that's good. It should create a mesh in just the horizontal direction, because we haven't done it yet for the corresponding directions part. Oh my god, you love to see it. Yep. So what we have right here is our horizontal mesh lines. As you can see, it kind of goes down. So what this is for each horizontal, what do we have first? For each horizontal Schmidt number, it creates those mesh lines. So what we have to basically do is the same exact thing. However, we're going to reverse these two. So we can literally just copy and paste this code because I'm lazy. So we're going to copy and paste, and then we just have to kind of flip these around right here. So we're going to have RE mesh corresponding to the Schmidt mesh. And then our parameters we have to switch around as well, because the parameters for them two numbers are definitely not the same. 2e to the third, and then we'll do 25 lines again. And then what were the parameters again? I keep forgetting. 0.6, 2.5, and we'll do 25 yet again. So everything else here should be exactly the same. The only thing we had to switch around was the Reynolds number compared to the Schmidt number, and then that should work. So Let's add those lines. Oh my gosh, no errors. Let's go. And then let's display our figure, see if it works. And it does. So here we are right here. Here is our lovely mesh with 25 lines in each respective axes compared to all of our data points, which have a little bit of error to them. But as you can see, stay on that pretty consistent path of an ideal path that the mesh represents. So here you are. Here is our model. It looks very nice. And this is what we're looking for. So this completes like part 2 of the exam. What we wanted to do was create we created 100 pseudo experimental data points. We had the 10% initial error at the very top of it. And then what we wanted to do was plot these points not only on the graph itself, but create a mesh of all the ideal values using the model that we created and be able to graph them out, which is what we have right here.